Good afternoon, everybody. Thank you for the introduction. So, as many of you may know, in HPC we are mainly using still like C and Fortran to program our computers. So in this talk I'm going to talk how to introduce functional semantics into this procedural code with the aim to improve the programmability and also improve while keeping the performance and also improve the portability. So during this talk, I'm going to discuss like what are the benefits that functional programming can bring to us, and how to make it exploitable in our HPC machines. Well, first I would like to introduce like what are HPC machines. So they are really big computer, much bigger than the usual desktop that you will have at home. And they're used usually for solving engineering and scientific problems. So the kind of problems we usually solve with these machines are limited by the hardware that we have. So before, you just could wait a bit, 1 or 2 years, then you bought a new computer, and it will just bring new CPUs, which had much higher performance than the previous one. But in the last like 10, 15 years, the frequency of the CPU cores is not really increasing anymore. And also the instructions per cycle is really slowly increasing nowadays. So how do we get faster computers, more powerful ones? Well, easy. We just add more and more cores. Or we use specific accelerators such as GPUs or FPGAs to offload some particular parts of our code. So this is, for example, the kind of machine that we have at the HLRS, at the Computing Center of the University of Stuttgart. This is a gray machine, which basically has 2,700 computing nodes. Each node has a different address space, so you have to communicate them through a network. Each node basically has 24 cores, real physical cores, with 128 gigabytes of RAM. The network is quite complex, so depending on how far you go in the communication between neighbors, you might need to go up to 3 different levels of network with different performances. And yeah, you need a very special big case to keep such thing, because it consumes like 3.2 megawatts, which you also have to cool down. So does this make sense at all if you want to accelerate a program? Is it enough just to add more cores? So probably many of you are already familiar with Amdahl's Law, which reflects like what is the performance speed up you can gain, depend on how your program looks like and how many cores you have. So basically, if you have some sequential part in your program that you can never parallelize, there is a moment where adding more cores will not improve your performance anymore. In fact, even if you have parallel parts, there is a moment that adding more and more cores will start degrading your performance. This is because classical programming models are usually geared toward reducing the computational complexity, but they often not take into consideration what is the cost of memory accesses and network communication cost. So what we want to do, and yes, we are lucky that we have a machine that just consists of CPUs. If you have accelerators, if you want to use them, then you need another specific language. You have to determine which is the parts you're going to move there, establish the communication with the rest of the program, and basically you have a machine that is very difficult to program, and once you tune your application for that machine, you will probably have to rewrite it again if you want to move to a different computer. So what we want to have is kind of a new programming model that is covering enough information for the compiler to be able to parallelize our programs, that will be able to exploit our specific hardware characteristics of our machines, and at the same make it portable to other supercomputers with different hardware. So up to now, how we introduce parallelisms in our machines, there are like three basic approaches. One is directly introducing it using the Linux P threads. You can also use MPI message passive communication through the network of the supercomputer. You could use already some enhanced programming languages, such Corel Fortran or UPC, which just show the whole memory of the computer as a global address space. Or you could introduce structural information of your application. This, for example, what people do with OpenMP, which is basically used to parallelize loop. You describe how your loop is, and it will detect how can it be parallelized and how many threads to get from it. Another language of this family is OmpSs, developed by Barcelona supercomputer, in which you describe tasks with respect to their input and output data. With this, the problem that OmpSs has is that you have, or even OpenMP, is that you treat the kernel of your body of your loops or your tasks as a black boxes, and you have no control, or the system has no control of what is the computational weight on it. It just relies completely on the information the programmer gave to it. So we want to explore new ways of extracting. We want to go this way with structural information, and but we want to make it better. So for example, this is what OmpSs creates, just a few tasks. It connects them through the input and output. Once it has a scheduler that is executing the task when once they can be executed. That means when their input is available. And yeah, it can grow into something very big, or even bigger than this, but it will not fit on the screen. But it's just a very flat structure, and nobody has any control of if one task is much more computational requirements than another one. So we are going to extract this in, what we want to do is extract this structural information not through the input and output, but annotating the code with higher order functions to give some functional characteristics of our code. They will describe the mathematics and algorithm we are trying to execute and let the compiler reason about what is going on. Why higher order functions? That's because they have a simple and clear execution structure. They are independent from the operator that is using them. And you can combine them to form real complex structures. At the same time, they can be transformed into other higher order functions that are equivalent from the computational point. You will get the same results, but they have different non-functional properties. So basically, we annotate with higher order functions, we extract the structural information, we reason over what they are doing, and then we can transform the underlying code that we had. Well, as everybody knows in this audience, so this is a map which has a very nice graphical structure, or a fold L, which has a different nice graph and simple. And what is going inside is not a problem. You don't need to care about it. We can define, like for example, this latest one is another higher order function that is not the standard one. We define it ourselves because it carries special information over the one we can later reason about. This is, for example, a stencil operation in 1D, very common in HPC, where basically you go through all the elements of your list or your array in case of C, and the values of your new list are dependent on your current position and the values of your neighbors. An example of transformations you can do with higher order functions is, for example, this fold L. You may be able to parallelize it and get the one on the top. You can partition it in different smaller fold Ls, and then the results make another reduction of it. If this transformation is valid or not, it depends on the mathematical properties of the operator you have. For example, in this case, to be able to do this transformation to be correct, the operation, in this case is this plus, has to be associative, and we also need to know what is the neutral element, which is the one that begins each of the partitioning. It looks like simple, and you can never know if this operation is going to be associative or not, because for example, in floating point operations, the plus is by definition not associative. Interchanging the computation over, even if mathematically makes sense, you will have a slightly, or you may have a slightly different results. If this result is valid or not for you depends on your code and your model. So you need a way to express this kind of information into your programming model. So the transformations have to maintain correctness, and we want to use them to be able to parallelize or to exploit other characteristics such as memory usage. Maybe you want to make sure some part of your code or your data fits into cache. Maybe you want to find the communications to your accelerators. So the higher order functions, basically, you can combine them in two different ways. As happened with OmpSs, you can combine them from the input-output dependency, or you can use them as operator. This leads to hierarchical structures where you can go in different levels. You can reason inside what is doing, so your nodes in the graph are no longer just simple black boxes that you don't know what's going on. So combining in these two ways of matching them, of combining them, you basically enable the modular construction of graphs of basically any size and complexity. Well, so this is basically what I call a flat structure, which is the output of one higher order function is the input for another one. So you have one node outside of the previous one. Also, we can already reason about the operator. I think that could not do with other programming models. Well, this is the code, but I will skip it. And this is a hierarchical linking between two higher order functions, where the map is using the fold as an operator, which at the same time contains other operators which could be other higher order functions. So your nodes in the graph are something you can reason over at different levels. So how to make this really work? So you need a very strong binding. You can read these annotations, you can reason over them, you decided more or less how to manipulate your graph. Now you have to reflect this graph on the C code, which is the one which is actually going to execute. So you have to make a very strong binding between the annotations and the C code. In this case, you have to indicate, for example, this loop in this function, which is called add all. It's just adding all the elements of a vector. You have to indicate which is the higher order function. You have to give a name of the operator, which is the body of the loop, is defined here with the plus name, and you have to say which is the input of the fold and where it's going to store the result in memory of your computer. At the same time, you need to express, you have to be able to express the mathematics not only for the simple C operators, but also for functions you will define. Because you might want to just define functions that operate through matrices, for example, or any other data structure that you want. For this, you will need custom functions. We are thinking of different ways. One possibility is ring, where basically you can set a set of operations which have certain properties between themselves. And, well, I'm not going to enter into here because it's a bit complex mathematical thing. Probably some of you are mathematicians and know more about this than me. And at the same time, another thing you need to make your compiler aware is about how the data is structured on the hardware memory of your computer. You need to specify things like, well, or the system to be able to make the correct transformations on the data structures. It has to know like what is the bit ordering, what is the endianness, how is the alignment of the data structures, if you are using a vector of structures or structures of vectors. And as it's usually communicating through a network, you have to be able to serialize it, deserialize it, and partition it correctly. The usual operations that are provided by the operating system are very poor. For example, malloc, you can just say the number of bytes you want, and there is no information about how the data is later going to be stored in it. So a simple example of how this is intended to work is, for example, the heat. We can use as an example the one-dimensional heat diffusion equation, where basically, imagine you have a 1D string, which is hot at some point, and you want to evaluate how it's cooling down, how the heat is spreading as time goes on. The same will work in 2D or 3D, but 1D is much simpler to see. First, you have to discretize your equation to be able to compute it. Here is like this stencil operation that we saw. It's like a certain element at some point depends on if the same position in the previous point and the neighbors. So this is a simplification of the code where you can basically annotate it. You define your kernel, which depends, you see here, in the array, the temporal heat map array is storing the information of that point. Well, it depends on that point in another array, plus the neighbors. This is defining a stencil operation around the whole array, and this is executed a number of iterations, which is each time step. From it, we can see a graph where you can go through it and you could reason. And for example, you can parallelize your data at different levels. So we could have the original vector running in sequential mode. We can partition it in a logical way without still going to any specific hardware. Each partitioning, we could partition it again as many times as we want. In this case, we can, for example, do two partitionings. The first partition is going to message level so that you can comment different nodes, and then inside each node, for example, can parallelize it again with OpenMP to exploit the many cores of each node. For OpenMP, once you have the partition, is quite simple. You just have to tell it that it's a parallel 4. In case of MPI, it's a bit more complex because you have to cut the arrays, introduce the neighboring from the communication to store the neighbor values of data that is in other nodes. So this is how the code looks like, adding the MPI and the OpenMP. And other things you can do is, these annotations are very near another functional language that is called Clash that are developing some of our colleagues that basically can convert these annotations that are very similar to Haskell into VHDL to exploit FPGAs. So that's all of what we are working right now and exploring. Thank you very much for your time.
Thank you, Daniel. Questions?
I don't don't know if I get it correctly, but you produce these pragmas to parallelize the code, yes? And these pragmas are a functional language. So did you compare the performance of such parallelized code by your pragmas or by, for example, MPI?
Well, so this pragma, so basically we use these annotations to know in which points we can parallelize. And then this is transformed to MPI. So what it executes at the end is MPI. We just use the functional annotations to be able to evaluate the program and analyze it.
So did you measure the performance of, do you have some results of any parallel program you measure, for example, speed up or effectiveness of such a parallelized program by your tool? Do you have such a use case? Because you showed this heat. So how it really parallelized? Did you measure speed up or effectiveness?
Well, right now we don't have a complete working tool, so we just parallelize it by hand following the steps the tool will do. The code is quite fine and scales well. So I could show you results or.
Thank you.
I think I was loud enough. One question, one comment. The question: if you say pragma ring something, you just promise to the compiler that the structure behind this behaves like a ring, yeah?
Yes.
So it can assume some things and so on and so on.
And that is applied to this data type. It could be a custom data type by the user.
But you can say, like in a loop, you can treat the code inside a loop as something you can split and apply fault in parallel. So I can imagine you can do something on a higher level like this. So you promise something to be a ring, so it has some properties you can use. And some comment to the previous question. It's very tricky to compare compiler with a human, yeah, because a human can write better or worse code, and compiler can be better or worse. So it's just a case who is better, yeah. And generally we want to save programmers' time and keep the efficiency reasonable rather than write the best code ever.
Thanks, Mikhail. Were you expecting a response from the... Do you want to respond?
Well, I didn't get exactly what is the question.
You just repeat it. I was asking about the ring, properties and so on.
Well, I didn't really understand what is your question. What is not clear for you?
It was, I was asking if when you write pragma ring something,
Mm-hmm.
to the compiler something behaves like a ring.
Yeah, so it means that these operations from this type has some properties, so it will enable or disable certain possible transformations.
Right. Last question.
So yeah, the directives you are using, they look very similar to what we can find already in OpenMP. So and generally speaking, you have to test the size based on the data size and so on. You have to test and make sure that it actually improves performance. Is there something kind of new that those techniques provide over OpenMP, to better optimize or to give better results?
Well, up to now, OpenMP can, well, I don't know the latest version, but I think it can only stay inside a node. So it cannot go through different memory address spaces of other nodes. And the other thing is that OpenMP is actually doing unparallelizing in the place you tell it to do. is not able to reason like, you cannot put like, if you have 3 different loops nested, you cannot annotate them all and it decide which is the best where to introduce the parallelization. Probably it will just parallelize all of them. Maybe you are parallelizing something that is very small and your performance will degrade. Here you don't force to parallelize, you have a system which is able to evaluate through the whole program where are the best points, where it thinks that there are the best points to introduce the parallelization and the communication.
All this emulation is done at compile time, yeah?
Yeah, it's a compile time it decides. It should need also a description of the machine to know, to be able to match the machine to the program you are trying to work on.
Great. Thank you very much, Daniel. The final speaker in the session is Nick.